right? So here you are learning properties of materials. So let's see what is a nanomaterial and what are the properties of a nanomaterial. And then the question, how big is this nano, right? And then you might have a question, why? Why really do we need this technology, right? And you might have heard some different words associated with nano, like nanoscience, nanotechnology, right? And so you will be wondering what is meant by these terms, right? And then, so as engineers, what are the opportunities available with nanotechnology? And can we make, in engineering applications, can we make use of these materials that we call the nanomaterials, right? So once we go through this lecture, you will be answering all these questions, right? So I'll move on. Now, so first question, what is a nanomaterial, right? So here I have taken an example. Have you heard about the fullerene molecule or the buckyball? Have you heard about it? I think you have heard about it. So this is a molecule with a special shape, actually with a spherical shape as shown in this figure, right? And it's made with 60 carbon atoms arranged in a nice spherical shape, right? So if you measure the diameter of this molecule, it is just 1 nanometer. So later let's see what is this 1 nanometer. So this is actually size of the buckyball, or the Buckminster fullerene molecule, right? So a particle like this, if you measure its size and if it falls to this nanometer dimensions, we call it a nanomaterial, right? So this is one example, this Buckminster fullerene. Right. So now then let's talk about what is a nanometer, right? I think you know it. So 1 nanometer equals to 10 to the power minus 9 of a meter, right? 1 nanometer equals to 10 to the power minus 9 times of a meter. That is a 1 billionth of a meter, right? Or 1 millionth of a millimeter. So think how small it is, right? So this is 1 millimeter, the smallest dimension you have in your ruler, right? So it's million times smaller than that, right? So this dimension, it actually we cannot see from our naked eye, right? It's very small, right? And then later we will be discussing about the challenges associated with this smaller size, right? So this is a very commonly used example, right? For help you to imagine how smaller these nanoscale dimensions are, right? If you take the size of the Earth, right, and the size of the football, the difference in the size of these two is actually same to the difference in size. I mean, how many times it is smaller, right? So Earth to football 10 to the power 8 times difference in size. The same size difference is there for the football to fullerene size ratio, right? So this size scale, therefore, since it's very small, since we cannot see it from our naked eye, right? And therefore, it's quite hard to manipulate these materials, quite hard to use. I mean, if you cannot see something from the naked eye, how you can assemble things to make useful devices, right? How can you see if something fails or if there's some defect? You cannot see from your naked eye, right? So this is quite challenging. Therefore, to work with these materials is quite challenging because it's very, very small, right? So, but still it gives you a lot of opportunities. So let's see what are those. Right. Now if your mother asks you what is nano, now how do you answer? Right. For a person that not from a scientific background, how can you answer? Anyone? Yes. Okay, so let's see. So nano is actually just a size scale, nothing but the size scale, right? So nano, that is what we call the nano scale. That is the size range from approximately 1 nanometer to 100 nanometers, right? So we already know what nanometer is. Now this nano is everything about the materials and their behavior in this smaller scale. And why it's so interesting? Because at this size scale, the materials start to, exhibit very, very peculiar properties. That means very strange properties than what we see in the materials we use day-to-day life, right? The bulk or the bigger size macroscopic materials that we use in day-to-day life, if we make their size that smaller into the nanoscale, they start to exhibit very different, very strange, right? And very useful set of properties, which we can effectively use in many, many different applications. And by using these strange properties of these materials, people have made many technologies advance, right? So in this lecture later on, we will be discussing about few examples and you will understand clearly. So now you know how to describe someone if they ask you what is nano, right? Okay, so now I want to give you a formal definition, right? What are nanomaterials? So this is the ISO definition on nanomaterials, right? So a nanomaterial, they define in two different ways, as you see in this screen, right? So either a nanomaterial we can describe as any material having external dimensions in nanoscale. So nanoscale we defined earlier. What is nanoscale? That is the size range from approximately 1 to 100 nanometers, right? So this is one type of nanomaterials. And the second type is that material may be a bigger, maybe millimeter size or micrometer in size, but having internal structure or surface structure again in the nanoscale, right? So now understand the difference between two, right? So the first one refers to a stand-alone object, which is if you measure any external dimension, at least one external dimension should fall into the nanoscale. And then the second definition, the material may be a macroscopic one, but then it has some internal structure or a surface structure. Again, if you measure some features, they are in this nanoscale dimensions. That means 1 to 100 nanometers. Right. So any questions so far? Okay, so we are good. Let's move on. Right. So these two types of nanomaterials, actually we give two names for them, right? So the first one we discussed, we call them a nano object, right? That is a material with any external dimension at nanoscale. And then the second type we have, that we call a nanostructured material. That means material can be a little bit bigger, but it has an internal structure or surface structure at nanoscale, right? So let's see some examples. Have you heard about carbon nanotube? I think you have heard, right? So this carbon nanotube is a tubular structure made with carbon atoms. So we will be extensively discussing about this material later in this lecture, right? So the diameter of carbon nanotubes usually few nanometers, right? So this is one external dimension. So we can call it a nano object. Also the buckyball we talked earlier, right? Because its diameter is just approximately 1 nanometer, right? So this is also a nano object. And let's see what is a nanostructured material, right? So these two pictures I show you. Can you see in the first picture, there is a line here, right? So this we call the scale bar, right? And the number here is 200 nanometers, right? So both these figures are micrographs or the microstructure view which we obtained from the scanning electron microscope, right? So one available in the Department of Material Science and Engineering, right? So here you can see the scale bar means this horizontal line length of this image is 200 nanometers, right? And you can see small tube-like structure in here. So if you see the diameter of one of these tubes, usually maybe 50 or less, 50 nanometers or less, sometimes maybe nearly 100 nanometers, some tubes, right? So this is an array of titanium dioxide nanotubes, actually a thin film made with an array of titanium dioxide nanotubes, right? So this is a bigger size film, but it has some internal structure which we can measure and which falls into nanoscale, right? So this is a nanostructured material. So you can see the side view of the tubes. This is a film made with the vertically grown array of tubes, right? So this kind of material, we call it a nanostructured material. And this material actually was synthesized by our own students in the materials laboratory. And they were going to actually use this material for supercapacitor applications, right? So later on we will discuss about these applications, right? So here I'm giving you one example of a nanostructured material, right? Now I think you have a good idea about what is nano size and what is a nanomaterial, how to define a nanomaterial, right? And now let's go to our next question. Why we need these materials? Now, as I told you earlier, I told you the same material, if I make that material into small size, into the nanoscale, it starts to exhibit very, unusual properties. Unusual, I must say, unusual yet very interesting. And also very useful properties than bulk. Bulk here means the macro size materials that we see every day, right? So here I give you one example. You know about graphite, right? It's a very common material that we use. In your pencils, you have a graphite tip. So not just the pencils, there are many applications of graphite. And that is not a very strong material, right? I think you know. That is not a very strong material. You can just, break it just with your finger maybe. So its Young's modulus is around 15 gigapascal. Right? And then there is a material called graphene. Do you know what is graphene? Again, very hot topic, very trendy topic these days. Graphene. Graphene is when you isolate a single layer from the graphite structure, right? So I think you have learned about the structure of graphite. Structure of graphite in school, maybe earlier. So it's like layered structure with hexagonally arranged carbon atoms, right? So it's a layer by layer structure. And if somehow, if you can, isolate, or if you can peel off one of these layers, right, just one layer of hexagonal carbon, we call it graphene. And then if you measure the Young's modulus of this graphene, it's 1000 gigapascal. See how large. I think the strongest material that is ever known is graphene. So graphene is just one atom layer thick, right? So its thickness is just less than approximately actually 1 nanometer. So the same material, graphite and graphene, same material. But when you have it in the nanoscale dimensions, you can see a very unusual increase in the Young's modulus. That means very unusual mechanical properties can be seen, right? So if you see the steel, the most common structural materials that we use, steel, right? So it has only 200 gigapascal Young's modulus. So this is 5 times higher than that. Right. So this is just one example about mechanical properties. But there are then other properties like electrical properties, optical properties, magnetic properties. In all these sectors, all these types of properties, this material exhibit very, very unusual behavior, which you can effectively use in many, many applications. Right. Okay, any questions so far? If you have questions, you can post them in the chat. And also B group chat, Nayanatara, please forward to me when there is a chat in the B group also. Right. Okay. So there is a question. If we divide a material to its atomic size, and then also we can have nanoscale of the same material. Sorry, I don't get it. If we divide a material to its atomic size, and then then we can have nanoscale of the same material. Is it also nanomaterial? Yeah. So if a same material, let's see, we have a piece of copper, right? If we make it smaller to atomic or few atom cluster size, then it will fall into the nanoscale. The same material, then we can call it a nanomaterial, right? So again, as I said, nano is just the size scale, right? So the materials that we have around us, right? Materials that we have around us, when we make it to the smaller size, they we can call a nanomaterial, and they will exhibit very different properties. As I told the copper example, the same copper material, their properties will be very, very different to the bulk, piece of the copper. Okay. So I think I am having other questions as well. I will answer the possible ones now and later on at the end of the lecture sometimes. What about diamond? Next question, what about diamond? Is its Young's modulus larger than graphene? Well, diamond also a very strong material. I think the Young's modulus almost near to 1 terapascal, right? Is it larger than graphene or smaller? I'm not sure. I think as I heard that the diamond is also maybe 900 to 1000 gigapascal. So maybe very similar, I think. But you can search, you can research about this material, right? Okay. Can we reduce temperature to make a material a nanomaterial? Next question. Well, to reduce a material size to a nanomaterial, there are many methods, right? So mechanically also you can do, but then you can control many external factors like temperature and pressure. Maybe you can make some, substance react with each other and make a nanomaterial and so on. But just by reducing the temperature, it might not be possible to make a material into a nanomaterial. But there are some complex procedures to do that, and some of them we will be discussing during this lecture. So next question, do chemical properties also change in nanoscale? Yes, of course, because the nanomaterial, if you see, the surface is very high, surface area is very high, and they have very high reactivity, and yes, they do exhibit different chemical properties. Is a real sheet of graphene also 1 nanometer thick? If so, why does it look like a thin sheet of paper? Did you see? Did you see a sheet of graphene? So how do you know it looks like a thin sheet of paper? So it's actually, yeah, less than 1 nanometer thick. And actually, it looks like a thin sheet of paper if you see it under a microscope, right? Based on its resolution, right? And if you use a microscope who can image the atoms like AFM, you can see the atoms also, right? But it will be something like wavy sheet of paper, right? Then, so another question, there are nanomaterial clothes or something, we can say that, but the whole material is high in size. Yeah, because they might have nanostructured materials in there, right? Because in nanoscale, nanomaterial alone is nothing. You cannot see, you cannot, manipulate. But when you use them in macroscopic devices, right, you still say that, okay, this is a nano item or nano device, right? But what's actually happening is something is in there which has nanoscale dimensions, and some function is there because of these nanoscale dimensions. Okay, so let's go to the lecture again. So I will answer, if there are more questions, I will answer at the end of the lecture, right? Okay. Now next question is actually whether this nano, is it a man-made thing, right? It's not, because in nature is the, most amazing creator that we have. It has some nanoscale, objects already, right? So one of these, nano thing in nature is this lotus leaf. Lotus leaf, if you have experience, it cannot be wetted by water, right? So if you spill some water on your table, it will wet the table, right? But the lotus leaf, as shown in the figure, if you spill some water on it, the water will stay as droplets. It will not wet the surface. right? So the wetting phenomena, I think you are familiar. So the wetting phenomena is associated with the contact angle that a liquid would make with the surface, which is in contact with the droplet, right? So if we have any droplet on any surface, if its contact angle is higher, right? Higher, that is greater than 90, we have low wetting. That means the droplet try to stay as it is without wetting the surface. But if the contact angle is less than 90, that can wet the surface. So we use two names, hydrophobic here for the, the non-wetting couples, and high wetting couples, we call them hydrophilic, right? So now coming back to the lotus leaf, why it does not wet? Now the contact angle actually depend on the surface tension of the droplet and also the surface properties of the surface. Properties of the surface plus properties of the droplet. Now here, if you see a microstructure of this lotus leaf, scientists have found that it has this small nanoscale spike-like structure, right? And because of these spikes, the water droplet cannot wet this surface, right? And its contact angle is around 146 degrees, very high value, right? So the scientists actually try to imitate this phenomena, and they see whether we can make some man-made surfaces like this, which has, spike-like structures. This kind of spike-like structures in surfaces, and whether we can make, super hydrophobic surfaces. For example, for the places that that is being wetted always, like, simply the household bathroom, right? If we have a surface that do not wet, we can, clean easily, because the fungus and everything will not be forming there, right? Or maybe if we have clothes, especially for the sportsmen, if they sweat, if they do not wet, it's really advantageous, right? So these kind of, useful applications are there. So people are learning from the nature, and they are trying to make these kind of materials for useful devices, or useful artifacts, right? And next example I take is this gecko adhesive system. I think you are familiar with this. So we have geckos in almost every houses in Sri Lanka. We have them, and I think you have seen them running in the vertical walls, right? Running up vertical walls. They do not fall, right? They have the perfect grip with the wall. Now the reason there is, again, if you carefully examine their feet, as I show in these figures, they have a nano hair-like structure, which can perfectly catch the small surface roughness in the wall, right? So any smooth wall they can climb easily. Smooth for our eye, but even if it's smooth for our eye, in small scale, again in that nano scale, it's quite rough, because in nano scale it has all the waves and bumps and everything, right? So this nano hair that this gecko has, he can catch those roughness features, right? So again, by imitating this kind of structure, people are trying to make adhesives, like plasters you use for medical purposes, right? People are trying to imitate these naturally occurring structures to make, devices that are useful for human, right? Okay, now we will come to a formal definition about nanoscience, right? So with all this, now I think you can understand this. Nanoscience is the study of structures and materials on the scale of nanometers. What does it mean? So science is always understanding, right? So nanoscience here is to understand the properties, for example, properties of a material when its dimensions are made into nanoscale. For example, to study about Young's modulus of graphene, or to study about chemical properties of copper nanoparticles, right? So you make a material into the nanoscale and try to study and try to understand the unusual properties that it would exhibit, right? So this is nanoscience. And then another word is nanotechnology. So these two are actually different, right? Nanotechnology is where we apply that knowledge we obtain from the nanoscience part, right? So we understand something about the material, right? About certain phenomena, certain chemical properties or certain mechanical properties, certain optical properties and so on. And we try to make use that property, right, in an actual device or actual artifact that we are using, right? By using those characteristics of a material that is in nanoscale. So by humans, by us, if we try to use those properties and make some devices work, so that is called nanotechnology, right? And then, okay, so you are engineering students, right? So for engineering students, why is it applicable? Is it for science students or only? Engineers, we work with a lot of macro structures, right? People make, automobiles, buildings, right? All sort of these very, very large structures, bridges, roads, right? Or maybe some plants, machinery. So that is the picture that you get when you talk about engineering, right? So can nano, does it actually fit with engineering, right? What do you think? And what is nano engineering then? It actually fits, right? When we talk about a few examples later, you will see. So most of the technologies, engineering technologies that we have been advanced, right, with the discovery of these nanomaterials, right? The same technology you can advance if you replace the conventional materials with nanomaterials, right? Even the, okay, let's say about the aerospace, aircraft maybe. In aircrafts, lot of materials are there, right? And people have made very, superior functioning materials for them by using this nanotechnology. So likewise, even if this is in the small scale, you can use these characteristics to invent new materials and thereby advancing the technology or the engineering design, right? Okay, so I will, I think I will stop here.